Okay, so hi everyone. My name is Austin Fang, and I'll be co-teaching calculus with my friend Ruthesh. So every single Friday, I'll be teaching from 4 to 5 p.m., and Ruthesh, he'll be teaching at a different time later on the week, and we plan on teaching the class for 4 to 5 weeks, so that counts to about 8 to 10 classes. If you guys have any questions or preferences, type in the chat. If you guys have any other, if you guys don't have any other questions, then I'll just jump right in, I guess. So, is there anybody in? Our first class is going to be on limits and continuity. And basically, a limit is the foundation for calculus because it's like the foundation of derivatives, which are like the true foundation. But anyway, basically what a limit is the value a function is approaching when x is approaching a certain number. It's not the exact value, but it's like the value that it's approaching. So let's say I have a function over here and we call it f of x, and we want to find where what's the value at 2 over here. We don't find the exact value, we find the value when x becomes very, very close to 2. So for example, 2.0001 or 1.999, etc. The formal definition is limit of x to c of f of x is equal to L if the right side limit or the positive limit is equal to L and the negative limit is equal to L. So here's some notation. When you're doing a limit, you're trying to find the point that you're basically finding a limit of. That's c, and the function you're using is f of x. For here, the little plus sign over here, that stands for the positive direction. So you're going from the right side and you're going towards the point. And for here, the minus sign stands for on the negative side, so you're going from the negative side towards the point. So we have two problems here, and I guess I'll walk through how to solve these problems. Is there anybody in? No, still nobody. Okay, so we see here that when we plug x is equal to 1 for the limit, we get 0 over 0. And in calculus, we call this indeterminate. So we want to figure out the limit when x is equal to 1, because we can't find the value. See, when we factor x squared minus 1 over x minus 1, we get x minus 1 times x plus 1 all over x minus 1. And we see for this section, for all x values that aren't equal to 1, this is equal to 1. And we also know that our limit is not exactly 1, but it's very, very close. So we can change this to 1. We can cancel it out because it's not because x is not equal to 1. So you get 1 times x plus 1, and now we simply plug it in to get 2. Does anyone? No. Okay. On here, we're trying to find the limit when x gets to 0, and we see that when we plug it in, we get 3 minus 3 over 0 is equal to 0 over 0, and that's indeterminate. So what we do is we multiply by 1, but more specifically, we're multiplying by the conjugate of this term over the conjugate in order to simplify it, so it's easier for us to work with. So we multiply by x squared plus 9 plus 3 all over square root of x squared plus 9 plus 3. And then when we multiply it out, we get x squared plus 9 minus 9 all over x squared times root times x squared plus 9 plus 3. Sorry for my bad handwriting, because like I'm typing on a computer. You can cancel these out, and then when you plug in x is equal to 0, we get 1 over 6. So where does a limit not exist? So there are 3 cases. One is when the positive limit does not equal to the negative limit. So let's say we have a piecewise function like this, and the positive limit from so the positive limit is equal to 4, and the negative limit over here is equal to 3. Since 4 does not equal to 3, we see that the limit doesn't exist. We see this is true because it directly contradicts our definition over here, which is that the limit is L if the positive and the negative side are both equal to L. Now, number 2 is when the limit is equal to infinity. So that's basically when we have an asymptote. So we have a graph here, and we look at x is equal to 0. We see that there's no actual value when we go on. Oh wait, that's a bad example, never mind. Let's say we have 1 over x squared, and when x gets close to 0, we see that on both sides f of x goes to infinity. While technically infinity, it exists, but it's not like a defined value, so we can't really count it as existing. And finally, it's when f of x oscillates between 2 known values. And oscillation is basically when it goes up and down like a curve. Now we have three different graphs here, and try to figure out which ones do exist, if the limit exists or not. So we're going to x goes to 0 for this one, x goes to 0 for this one, and x goes to infinity for this one. Okay, cool, we're done. We see for here, when x gets to 0, it oscillates between 1 and negative 1. So when we get to 0, the value of x oscillates between 1 and negative 1, so there is no definite value for x. So the limit does not exist because of the third property. Now for here, we see that it oscillates, right? Since it goes up and down, but it doesn't oscillate between 2 known values. In fact, it kind of decreases, and we'll go over this problem later, but we see that the limit exists even though it oscillates because it's not between 2 known values. And finally, when x goes into infinity, we found the limit for this one. We see that the limit doesn't exist because when x goes into infinity, sine x has a period of 2 pi, so every 2 pi it goes through a new period, and we see that the limit doesn't exist because it oscillates. So we have another example here. So try to find the limit when x is equal to 2. Well, we see that the positive limit of f of x, so lim at x goes to 2 plus over here, is equal to, that looks kind of like 5/8-ish of the f of x. Okay, pardon my bad handwriting. And then the negative for f of x is equal to 4. So because limit of x to on the negative side of f of x is not equal to the limit on the positive side of f of x, we see that the limit does not exist. So here are some properties of limits. If you have two functions, f of x and g of x, the limit of the sum of the functions is the sum of the limits. And then the same thing for negative, except for we're subtracting. And the way we prove this is, let's say we have an h of x is equal to negative g of x. We see, since we flip the function vertically, right? Let's say we have a limit over here. The limit of the same of h of x at the same point is going to be negative m. It's going to be negative m. So when we do so basically this is equal to f of x plus h of x. So, and then it's L plus h, but h is equal to negative m. So that's how we prove this. Now for this, for the third property, is when you multiply the limit of the product of two functions is equal to the product of the limit, and we can prove number 4 using 3. So let's say we have a function, a constant function, y is equal to k. We see that the limit at any point is going to be m is equal to k, because and then we can just plug in y is equal to k for f of x and k for m. And then number 5, what we do is we create an h of x that's 1 over f of x to prove it using 3. And number 6, you should just memorize this one. It's so the limit of a function raised to a power is equal to the limit raised to a power. Now here are some techniques for limits. So direct substitution. So what you do for this is you directly substitute a value such that it doesn't reach indeterminate form. So let's say I have limit of x goes to 2 of, let's say, 3x plus 4. And we plug it in, we get 6x, we get 10. And then if you get a constant over infinity, then the limit is 0. We can see this because when you have, let's just say infinity is a really big number, right? And then infinity has infinite multiples of the constant. So so you cancel out the constant, you get 1 over infinity. And 1 over infinity gets very close to 0. The same thing for this is if you get infinity over a constant, the infinity is infinity times the constant. So the limit doesn't exist because it goes towards infinity. Special limits, we'll get to these later. Indeterminate forms, as we saw with some of the first examples, you have to do some manipulations like cancel common factors. Let's say you have x minus 1 over x minus 1 times x plus 2 over x plus 3. And you're looking at the limit when x is equal to 1. You cancel this out because if you don't, you get indeterminate form. Multiply by the conjugate. So typically if you have like a square root plus something, you multiply the conjugate, because it's really hard to deal with square rooted, those kind of terms. Divide is basically like cancel common factors. And then change absolute value functions into piecewise functions. Number 6 we'll get to later on in this chapter in this class. And number 7, just don't worry about this for now. So for some examples. Number 1, we see that we have the limit to x to the pi fourth when secant of x is squared. So we can do direct substitution for this one. because there is no indeterminate form or some sort of 0 over 0 thing going on. So what we do is we directly plug it in. So we get 1 over cosine pi over 4 squared, and that's basically root 2 squared is equal to 2. And then let's look at number 4. So when x goes into infinity, 1 plus 1 over x goes to 1. However, this is actually not the case. You'd expect it to go to 1 because you get 1 when you plug in x goes into infinity, you get 1 to 2x. So you expect to get 1. However, this is not the case, and we'll come to this later on. Number 2, so the limit when x goes into infinity of 3 times e to the negative x. So we can rearrange it to get 3 over e to the x. And when x goes into infinity, e becomes very, very large. So it's basically equal to 3 over infinity, and that's equal to 0. Keep in mind when you're doing the actual AP exam, do not use infinity or any kind of indeterminate form like infinity over infinity, 0 over 0. Do not use these because I guess they're kind of like illegal. So for number 5, we do the same thing, sort of. So 20 over 4 plus 1 over e to the x. 1 over e to the x. Plug in infinity, we get 20. It's approximately 20 over 4, and that's equal to 5. Here's some more. Now we're going to use manipulation. We're trying to multiply by the conjugate in this case, which is root x plus 1 all over root x plus 1. And we multiply these two out, we get the difference of squares formula. So we get x plus 1 minus 1 all over x root x plus 1 plus 1. Cancel these two out because they're both equal to x, and we plug in 0, we get 1 over 2. Now, we from the techniques, we know that for absolute value functions, we should break them up into piecewise. And since we're doing the positive limit, so coming from the positive side, we are thinking of using when x is greater than 4. So when x is greater than 4, our piecewise becomes x minus 4 over x minus 4. And that's just simply 1 for all values. So we get our limit is equal to 1. Next, we're going to learn about the squeeze or the sandwich theorem, and that is the technique number 6 from earlier. And this isn't really common in the exam, but you should just know it because it's in the curriculum. So let's say you have a function, you have 3 functions, h of x is less than f of x is less than g of x in an interval that contains x is equal to c. And the limit of h of x is equal to the limit of g of x, which is equal to c. Then we see that the limit of f of x must equal to c. So visualize it like this. So we have 3 functions, for example, and then this is h of x, f of x, and g of x, respectively. And h of x and g of x both go to a certain value c, right? So it's basically like squeezing f of x into c because f of x is in between h of x and g of x. So we have a function over here, f of x is equal to x cosine x, and g of x is equal to absolute value of x, and h of x is equal to negative x. We see that absolute value of x is always greater than x cosine x, and h of x is always less than x cosine x. This is because because cosine of x has a period of 1 to -1, and you can derive that you can simply derive that h of x is less than f of x is less than g of x. You can do the proof by yourself later, but that's not really the point here. We're trying to use a graph. So in the graph here, you see that you have g of x here. You have h of x over here, and then you have f of x is all over here. We know that the limit for absolute value of x and absolute value of negative x at 0 is 0. So using the squeeze theorem, we see that f of x, the limit at x is equal to 0, must be 0 too. So special limits. So when you have these limits, you have to realize they're special cases, and it's really hard to prove them now. We might get to it later in future chapters. You just have to memorize these. So limit as x goes to 0 of sine x over x is equal to 1, and you do this the inverse. What's it called? When you flip the numerator and denominator around, you also get that it's 1. 1 minus cosine over x is equal to 0. The limit when x goes to 0 of 1 minus cosine of x over x is equal to 0. And the limit of 1 plus x to the 1 over x is equal to e. And limit of x to infinity of 1 plus 1 over x to the x is equal to e. So let's prove the second one, the second special limit, using the first one. Okay, so you have 1 minus cosine x over x. And then you multiply by the conjugate, which is 1 plus cosine x over 1 plus cosine x. And you get 1 minus cosine squared x, which is equal to sine squared x. So you get sine squared x over x times 1 plus cosine x, so is equal to sine x over x times 1 plus cosine of x. And sine x over x is equal to 1 because it's our special limit. And sine x over 1 plus cosine x is equal to 0 because when we plug in x is equal to 0, we make a direct substitution. We get 0 over 2, which is equal to 0. So so we've proved the second special limit. Now, number 3, we can't prove the first one, but using this first part of the third special limit, we can prove the second part of the third part. Okay, I'm confusing myself. Let's say we let u is equal to 1 over x. So basically what we do is we plug u in for x. So when x gets to 0, u gets to infinity. So when x gets to 0, u becomes very, very big. So we get limit of x to 0 is basically the same as limit of u goes into infinity. And then we have 1 plus x. We replace that with 1 over x because that's what u is. And then 1 over x, 1 over u is equal to x. So in the end, we get that these two are in fact equal, except for in this case, we just substituted a u, which is equal to 1 over x, to get the second one. Sorry if it's kind of confusing. So horizontal asymptotes. So I think you guys should already know most of the stuff about asymptotes because you guys learn it in like Algebra 2 and Pre-Calc. But a horizontal asymptote occurs when the limits of function at positive and negative infinity equal a constant c. When the numerator's degree is less than the denominator's, the asymptote will be at y is equal to 0. So let's prove this. Let's say we have axn plus bxn minus 1 dot dot dot, and we have axn plus bxn minus 1 dot dot dot. We see that, n plus 1, sorry. We see that this term is a dominant term. So when we let x go to infinity or negative infinity, this will be the biggest term out of all the terms. So when x becomes very, very big, all these terms will be insignificant. So it'll be 1 over infinity, and 1 over infinity, the limit is 1 over infinity, which is equal to 0. And for numerators and denominators with the same value, the asymptote is the ratio. So let's prove this. So we have axn plus dot dot dot, and then we have capital axn plus dot dot dot, right? So when we let x become super big, we see that all these terms over here, they're all insignificant compared to these two dominant terms. So when x goes to infinity, these terms will be very tiny in comparison. And then basically all you do is cancel it out, and you get a over a. Y is equal to a over a, which is the ratio between the coefficient of the highest degrees in the numerator and denominator. So I guess I'll just do this example on the next slide because there's not enough room. New slide. Give me a second. So x sine 1 over x. Now, what does this kind of look like? So remember our special limit, sine x over x. The limit when x goes to 0 is equal to 1, right? Now, we see this kind of the same. It looks kind of similar because they have sine of x and they involve 1 over x somehow. So we're trying to like relate these two equations together. And this is x goes to infinity because the lim when x goes to infinity, because we're trying to find the if there's a horizontal asymptote or not. So let's replace let's replace this x with u, and let u is equal to 1 over x, right? So when x gets to 0, u becomes infinity. So this is equal to limit u goes into infinity. And then sine x over x is sine over 1 over u over x. So u is equal to 1 over x. So it's 1 over, sine 1 over u over 1 over u is equal to u sine 1 over u. So we proved that these two limits are the same. So we see that x sine 1 over x should also equal to 1. And we see this is true. This is true for the positive, but also when the limit from the negative side, when we account for that, u also goes to negative infinity. So on both sides, u goes to 1. So the graph, so both sides they go to 1. So this is 1. Okay. Slant asymptotes. Slant asymptotes occur when the degree of the numerator is greater than the degree of the denominator by exactly 1. We see here that the asymptote is a linear function, and it's precisely the quotient after dividing the numerator and the denominator. So let's use this example over here. We have x squared plus 3x plus 4 over x plus 2. Let's just use long division. X squared plus 3x plus 4 and x plus 2. So 1 over here, we put x over here, so x squared plus 2x, subtract, we get x plus 4, so plus 1, and then we subtract x plus 2, we get 2. Now we see that the slant asymptote is x plus 1, but we should also wonder why the slant asymptote doesn't really use 2x plus 2, 2 over x plus 2. It's because when x goes into infinity, this term becomes negligible in comparison to this one, because it's 2 over infinity, which is equal to 0. So that also explains why the function will never touch the slant asymptote, because it has this term 2x plus 2 to ensure that it'll never touch it. It'll never actually equal to x plus 1. Now, vertical asymptotes are when the denominator, so our denominator is some x minus a times x minus b dot dot dot, it occurs at all the zeros of this polynomial. This is because when the denominator gets close to 0, the limit when the denominator gets close to 0 of the fraction, it becomes really big. However, you also need to account for holes. Holes occur at values when the roots of the numerator and the denominator coincide. So let's say, so find the holes and the asymptotes of this fraction. I'm not gonna do an actual polynomial. I'm just gonna write it out in the factored form. X minus 2. Okay, so we see here so the possibilities are 2, 1, and negative 4, right? 2, 1, negative 4. We see that only for 2 does the numerator also become 0 when we plug in 2. So when x is equal to 2, we get a hole. For x is equal to 1 and negative 4, we get asymptotes because the denominator is 0, while the top is a value that's not 0. So we don't get an indeterminate form. So at x is equal to 1, 4, we get 1 and 4, we get asymptote for vertical. And also let's account for horizontal asymptotes. We see that the degree is bigger on the bottom, and from what we learned before, if the degree is bigger on the bottom, then the horizontal asymptote will be y is equal to 0. Horizontal. So let's look at end behavior. So end behavior is basically looking at the limits when it goes to positive and negative infinity. Left end behavior is the left side, so negative infinity, and right end behavior is the positive side, the right side. So we look at positive infinity. So we have function e to the x. So let's graph this. So it looks kind of like that. So we see that when e to the x goes to limit when x goes to negative infinity, right? E to the x is equal to what becomes, let's let u is equal to negative x. Limit of u goes to x goes to negative infinity, and then u is equal to x. U goes to infinity of 1 over e to the u. And then we see that it's basically 1 over infinity, and then it becomes negligibly small, so we get this is equal to 0. On the positive side, we see that when limit of x to infinity of e to the x, the right hand behavior. So this is a left hand behavior, and this is the right side. We see that e to the x is exponential, so when x becomes very large, this goes into infinity. So it goes, and the limit is equal to infinity. So we say for left hand behavior, x goes to 0, and for the right hand behavior, x becomes very, very big. So now we go into continuity. So we say a function is continuous if the limit is equal to the value. And then we say the function is continuous on an interval when it's continuous at every number in the interval. A function is continuous at an endpoint when the limit at one side is equal to the y value of the endpoint. So let's say, I guess we have 3 cases. So here we have like a function. However, there's a hole in the middle, and it's redefined to another point, to another y value. We see that the limit does not equal to the value because there's a hole at where value should be in order to make it continuous. So we call it, so this is non-continuous. Let's say we have a function over here, and there's a hole at the top. We see that it can't be continuous because there's no limit to begin with. So the value can't equal the limit because the limit doesn't exist. So this is non-continuous as well. And finally, we have like a function over here. We see that the limit and the value coincide, so it in fact is continuous. And then let's look at the endpoints. So let's say we have a function. Let's take this function again. So on the left endpoint, let's say we redefine the redefine the value over here, and there's a hole. So the limit from the positive side over here is this point over here, but the actual value is this point. So we see that it's not continuous at the endpoint. And then on the right side, let's say the value coincides with the left hand limit, so the negative limit, then it's continuous. So we say this function is continuous from so exclusively on the left side and inclusively on the right hand. So it looks kind of like this, and let's say this value is a and this value is b. So we can say that this function is continuous from a to b, not including a but including b. So discontinuities. There are 2 kinds of discontinuities, removable and unremovable. Removable is when we can take the discontinuity and we can redefine it. We can redefine the single point to make the interval continuous. An unremovable continuity is where we can't redefine the point to make the function continuous. And polynomial, rational, exponent, radical, and trigonometric functions are all continuous for every number in their domain. But like piecewise, or like step functions, ceiling functions, floor functions, they can be continuous, but they can be non-continuous as well. So let's look at removable discontinuity. So we have our function, right? There's a hole here, and our value is over here. What we can do, this is removable because we can take this value, we can redefine it to be on this function to make it continuous. A non-removal of discontinuity is like if we have a piecewise and the value is on the bottom one, we can move it up here, but it won't be continuous. There's no way we can make this continuous without affecting the right side, but we can't do that because we can only redefine a single point. So we say this is non-removable or unremovable. Finally, for this section, we're going to be talking about the intermediate value theorem. This is a pretty important topic for this chapter. I think it's one of the main things they'll probably talk about. They'll probably test you on the exam. IVT. It's also short for IVT. So in a function that's continuous on a closed interval for a number between the y values, these two y values, and let's say it's k, let's say this is k, right? There must be some f of c on this closed interval that is equal to k. So in the AP exam, you must state that the function is continuous. I'm pretty sure they'll get rid of some of your points if you don't, and I don't think you want to do that. It's a really easy way to lose your score, decrease your score. So a good way to visualize this is, let's say your function is like a rope, right? Your rope, you can morph it, you can like twist it, you can turn it, you can do all these weird things to it, but you can't cut it because we're saying our function is continuous, right? And then we have this barrier, I guess, and then your endpoints are on two sides. There's no way that your rope can go around this barrier because it extends to infinity. So that's kind of like the informal proof of IVT. It's like you have a rope and you can like extend it however much you want, except for there's a barrier and you can never get around it because it extends to infinity. So let's prove x squared is equal to 4 at some point without directly calculating the x that gets you of f of x is equal to 4. New slide. So let's take 1 and 3. Okay, so let's say let's take the interval of 1 and 3. Now we see f of 1 is equal to 1, f of 3 is equal to 9. We state x squared is continuous. You have to do this in the AP exam, well, because they'll deduct points. It's like 1 point if you do, but 1 point is a lot in FRQ, so you should probably state it. So we see here in our function, I guess, so this is 1, 1, and this is 3, 9. So by IVT, so by IVT sense, 4 is between 1 and 9. There must be some value. There must be a value such that there's a value such that x squared is equal to 4. And obviously we know it's equal to 2, but you need to state that x squared is continuous. So I guess we'll move on to derivatives next. So derivatives. Oh god, the quality is kind of dying. Oh, whatever. Okay, so derivatives. So, so derivatives are basically like the foundation of calculus. Everything that's calculus requires derivatives or antiderivatives. So, to understand derivatives, we first need to understand average rate of change. Average rate of change. So the average rate of change in an interval is defined as FB minus F of A over B minus A. And that looks a lot like the slope formula. So basically, it's like the slope of a function. It's a slope between 2 points on a function. And it's the average slope of a function. In the AP exam, when they ask you to calculate the average rate of change, how I represent an equation is I say average AVG rate of change, and then I write out the formula. You should, when it comes to the AP test, you should write out all the formulas you use. So you write out the formula, and then you plug your values in, and then you get your average rate of change. So in the AP exam, make sure to put all your work, even if it seems kind of useless. Obviously, you don't need to do the super obvious things, but make sure to show most of your steps. So calculus is basically finding the average rate of change on a tiny interval. So you have this interval right here, and it's getting smaller, 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 smaller. When it gets super tiny, when the limit of B minus A gets to 0, we get the instantaneous rate of change, which we call the derivative. It's essentially the slope of the function at single point, and specifically it's the slope of the tangent line when you at that point of a curve. So we can find the derivative using two formulas, and we call these formulas the definition of a derivative. So the first one is the limit of f of x minus f of a over x minus a, and let's say we have f of x, this is x f of x, and you have a curve over here, and let's say this is a f of a, and then basically how we visualize it is a gets close to x, and slowly our tangent line and our derivative matches up with the tangent line. Because a tangent line is when it only touches the function at one point, and eventually a and x will coincide when b minus a gets to 0. And then this is basically the same as the other one. I personally prefer using the second one, f of x plus h minus f of x over h, but lots of other people use the first one. I would recommend using the second one, but it's all up to you. And we can see here, so we have x, and then we have h, and then we're decreasing, and this is f of x plus h minus f of x, right? And then h becomes really small, so our tangent line, so our line soon matches with the tangent line. So find the average rate of change for f of x is equal to 2 plus cosine x over the interval of 0 to 2 pi. So cosine x of 0 is equal to 1, and cosine x of 2 pi is equal to 1. So we see that f of 0 is equal to f of 2 pi. So let me write it out. So average rate of change is equal to FB minus FA all over B minus A, right? And then we have to write down, oops. So the limit of when, actually never mind, I'm dumb. It's not the limit, wrong thing. F of B minus F of A all over B minus A is equal to F of 2 pi minus F of 0 all over 2 pi. This is equal to 3 minus 3 or 2 pi, and we see that's equal to 0. So the average rate of change is 0. Now let's do the average rate of change. So for the second problem, the height of a rocket is 3t squared feet, where time t is in seconds. Find the average rate of change between 0 and 10 seconds. Okay, so we say that the average rate of change is equal to F of B minus F of A all over B minus A is equal to F of 10 minus F of 0 all over 10. 3 times 10 squared is equal to 300, and then F of 0, so time is equal to 0 minus 0 all over 10, so we get 300 over 10, and we get the average rate of change is 30 feet per second. Try to remember to put in your units. I don't know, I don't think they deduct points, maybe they do, but it's still better to put it in just in case. So we should try to further understand derivatives, because derivatives, it's really important for you to fully understand it, because they're really like the foundation of calculus. What derivatives, they measure the rate of change of your function f of x. We say that a function is differentiable at a point if the derivative exists, and the function is differentiable on an interval if every point, excluding the endpoints, is differentiable. A function, well, the endpoints can be differentiable, so I guess, but like if you have like a function like this, and it's like a piecewise, so these, so there's nothing over here and there's nothing over here, you can't really calculate the derivative. You can't really calculate the derivative at the endpoints, but we still say that this interval from, let's say this is A and this is B, we say A comma B, and we say this interval is differentiable. There are multiple orders of derivatives, and the first measures the slope of the tangent to a function. So you can have a second order derivative, a third order derivative. Usually we only go up to the second order. So we write the derivative as f prime of x or y prime or dy dx or d dx of f of x or capital D d f of x or dx f of x. You rarely will ever see the latter two. Just remember these. These two are pretty much interchangeable, and you usually use dx f of x when you want to write out the full function, and dy dx is when you don't want to write out the full function, I guess. So for multiple order derivatives, what you do for the notation is you f, for the second order you f double prime x, or third, you do three of the prime symbols, and then for y prime you do 2, and then y prime, and then y double prime, then y triple prime. And so basically for the nth order derivative, you add that many of those marks. Or sometimes I guess people will write f2 of x or f3 of x. I personally like using f2 of x, and I think that's how most people do it for higher order. So it'll be kind of confusing for these ones, but so for dy dx, it's d squared y over dx squared, and that's basically all you need to memorize, because you won't use you rarely will use higher order derivatives, and if you do, you definitely won't use this notation. So just memorize d squared y over dx squared. Yeah, so that's like all the notation you need to know. So let's use the definition of the derivative to find the derivative of 2x squared minus 8x, and find where the function is increasing, decreasing, and where the tangent line has a slope of 0. Then graph to verify your answers. Okay, so limit of h to 0 of f of x plus h minus f of h all over, minus f of x all over h is equal to it's 2. So we subtract, so we get 2x plus h squared minus 2x squared. So we get 2 times x, we get 2, we get h squared plus, and then so x plus h, so you get 2xh. So you get 2 times 2xh plus h squared. H squared. And then for the minus 8x part, it's minus 8, minus 8, so so it's minus 8, x plus h minus f of x, so we get minus 8h. And then you divide that by h, cancel out h, and we get is equal, you're supposed to, sorry about that. Make sure you put limit for all of the parts that you don't, for all the parts that still involve a limit. Like, I still have an h term here, so I need to remember to keep the limit when h goes to 0 part of the equation in. So we get 4x plus 2h minus 8. Now we plug h in, and we get 4x minus h, because we directly substitute h, which is 0, and this is equal to 0, so 4x minus 8. And 4x minus 8 is equal to, so 4x minus 8 is equal to 0 when x is equal to 2, so x equal to 2, f prime of x is equal to 0. We see that when x is less than 2, f prime of x is also less than 0. And then x is greater than 2, f prime of x is greater than 0. So let's take a piecewise function. So it's equal to x squared when x is greater than 1, and it's equal to 2x when x is less than 1. And let's decide whether the function is differentiable at x is equal to 1. So we need to remember that that in order for a function to be differentiable, I think I skipped over this, but a function must be continuous to be differentiable. Okay, so if a function is non-continuous at a point, the point will never have a derivative. So let's first confirm that it's continuous for the first part. So plug in x is equal to 1, so we get 1 for x squared, and then for 2x we get 2. So you see that 1 does not equal 2. So it's non-differentiable. Non-differentiable. And how about when x squared, how about a piecewise function equal to x squared when x is greater than 0 and equal to 0 when x is less than 0? So for piecewise functions, let's say we have two functions here, and then this is a separate function. We want to take the derivative at, let's say we have a point C, take the limit of the derivative on the right and the left side, and if they equal to each other, then the function is differentiable at that point. So x squared, to save you guys time, the derivative is 2x, so at 0 we get 0, and then y is equal to 0. It's constant, so obviously the derivative is going to be 0. 0 is equal to 0. We need to confirm that it's continuous, so when x squared is equal to 0 squared is equal to 0, and y is equal to 0, 0 is equal to 0, so continuous, it's continuous, and it's differentiable. So it's differentiable. The main thing to remember for these piecewise functions is when you're, first of all, you need to make sure that at the point it's continuous, and then you need to make sure that the derivative, the limit of the derivative when you get to the point on the right and the left side, on these two sides, the derivative, the tangent, the slope of the tangent line, make sure they're equal, or you'll get a corner. So like here, let's say we have y is equal to x squared, and then you have y is equal to negative x. There's a corner here. And in our next slide, we'll get into areas where derivatives don't exist. So they don't exist at corners, discontinuities, or vertical tangents. We say a function is non-differentiable at a point where the derivative does not exist. So other than memorizing these, here's like my way of showing that these aren't derivatives. So you have a corner here, right? Try to draw like the tangent line, right? We see the tangent line is where the function touches that one point at the point x is equal to c, right? There are like infinite amount of tangent lines at this point, so since they're infinite, you can't have multiple derivatives at a single point, so because that's how derivatives work. So that's kind of how I visualize how corners don't work. Now let's say we have a discontinuity. Earlier we stated that if a function isn't continuous at a point, it can't be differentiable either. Like another way of visualizing it, so let's say even non-removable, and our point is over here, you can like kind of like rotate your tangent, so there are like infinite amounts of tangents, I guess, and so that means the derivative doesn't exist. And then if you have a removable one over here, you can just pivot it into a million ways. And since a point can't have multiple derivatives, we see that the derivative doesn't exist. Now, a vertical tangent, you may be thinking that vertical tangent and discontinuities, vertical tangent is a discontinuity, but there are some functions that have continuous vertical tangents like this one. And we see here we use the same method, infinite amount of tangent lines, and there can't be multiple derivatives, so it does not exist. So show that they're not non-differentiable, these two functions. So for x plus 1, we see the function is like this, when x is equal to -1, right? There's a corner here, so it's non-differentiable. X minus 2 over 2/3, I'll have to graph that one. Where Desmos x minus 2 to the 2/3. Okay, so we see that the function is like this. It's a vertical tangent over here, so it's non-differentiable. X this out too. Tangent lines, so we know that the derivative is the slope of the line, and all we need to do is now find a point. But luckily we know that the tangent line goes through the point, so we have, let's say we have f prime of c, and then we have c comma f of c, the point. All you do is you just do point slope form. Try to not change it to standard form. Do not do y is equal to mx plus b and other forms, because it's just wasting your time. The point slope form is easier on the graders, and you definitely won't make a mistake. And just to remind you guys, it's y minus y1 is equal to mx minus x1. And x1, y1 is, this is x1 and y1. So let's find the tangent line for sine of x at pi over 4, and let's do the same for cosine x. Find the derivative of sine, we need to find the derivative of sine of x at pi over, of sine of x, sorry, we need to find the derivative of sine of x. So limit as h goes to 0 of f of x plus h minus f of x all over h is equal to sine x plus h minus sine x all over h. Oh, I forgot to put the limit. Don't forget to do that. Is equal to limit as h goes to 0 of sine xh plus, I guess I'll continue over here, all over 8. Why is my pen not working? Oh, draw all over h plus cosine x sine h minus sine over x. We see that we can plug h is equal to 0 into this this term, and we get sine of x. And we have a sine of x to cancel it out with. So we get, in the end, we get cosine x of sine h all over h. Sine h over h, when h goes to 0, we know that it's our special limit. So we get its cosine of x. Cosine of x at pi over 4 is root 2 over 2. And the point of pi of sine of x with the x value pi 4th is pi 4th comma root 2 over 2, and then our tangent line is y. It should be y minus root 2 over 2. Y minus root 2 over 2 is equal to root 2 over 2. That's our m times x minus pi 4ths. Right. So that's our answer. Now let's try to find the derivative of cosine x. Now cosine x is equal to sine of x plus pi half, right? So we see the derivative of sine of x plus pi halves is equal to, we take the, when we f prime all of this, we get is equal to cosine x plus pi halves, because we're substituting x plus pi half for another value of sine x. So we get cosine x plus pi half, and cosine x plus pi half is equal to sine x. So we see that f prime of cosine f prime, oh wait, actually don't write f prime, it's it's d dx, that's my bad. So d dx of cosine x is equal to sine x. And then we do the same thing. So no, it's equal to, oh no, x, never mind, sorry, it's negative sine x. My bad. So we see that cosine x plus pi half is equal to negative sine x. So d dx of cosine x is equal to negative sine x. And then we find the derivative is equal to negative root 2 over 2. So y minus root 2 over 2, because cosine of root 2 over cosine of pi over 4 is root 2 over 2, is equal to minus root 2 over 2 times x minus pi fourths. Right, and then here are some general differentiation rules. Constant functions, the derivative is 0. We see that the tangent line, if we make a tangent line to this, it's completely flat. So look for constant functions, the derivative is 0. Power functions, the derivative is n times x n minus 1. This is, so we can prove it. So I'll just, okay, so lim h of 0 of f of x plus h minus f of x all over h. In the end, when we cancel out the x to the n terms, we get x times h times x times n minus 1 times x dot 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 all the way to x to n. So there, I mean, there's no h here. There are h of the, there are n, wait. Okay, I'm confusing myself. Never mind. So there's h, it's h times this over n. We see there are n terms because our terms are split into two sections of x's, and on the left side we see it goes from n minus 1 to 0, so there are n terms. So when we cancel out the h, and we cancel out the h, we get n of these x n minus 1, because n minus 1, because all these terms multiply to x to n minus 1. Constant rule on d dx of c times f of x is equal to c times f prime of x, and the sum and difference form, the sum of the derivative of the sums of two functions equal to the sum of the derivative, and for difference, the difference of the difference of the two derivatives is equal to the derivative of the two functions. That's the tongue twister, I guess. So the product rule, quotient rule, and chain rule, I advise you to memorize all these. So f of x times g prime of x plus gx times f prime of x is equal to d dx of fx gx. For the quotient rule, this is really annoying to memorize. To derive it, you just do let g of x is equal to 1 over h of x. We don't have enough time to memorize it, but essentially how people memorize it is low d high minus high d low over low squared. It's kind of weird way to memorize it, but it definitely works. Chain rule is we get that dy dx is equal to dy du times du dx. So let's say we have a function 2x minus 3 to the 4th power. So basically what we have to do is we take, since 2x minus 3 is inside of x to the 4th, what we do is we find the derivative of x to the 4th and we multiply it by the derivative of 2x minus 3. And that's what the chain rule is. So on the next class we will go over some examples of the product quotient rule, chain rule, and some of these general differentiation rules. Ruthesh will cover these more in depth. Thank you for joining. If you guys have any questions, if you want me to, any preferences, if you want more practice problems, just email me later. And I think that'll be it. Remove